Good evening, children. Once again, the happy Onam to all of you. Why? Because we are celebrating Onam today. So let us begin with the fourth one, case study, the fourth unit, electromagnetic induction and alternating current. So I welcome you to One Mark Solution. Please like, share, and subscribe if you are really interested in it. Anyway, now long back we have started, and thank you for our Sir Dr. Azad. Why? Because the person behind this is Sir. Once again, thank you, Sir. And children, we have started long back. Now you can go through these questions, especially AR, that means assertion reason, and the case study is also there. Not only that, one marks, so many questions also there, MCQ is also there. So you can just go through it. Anyway, it will help you, sure. So let us move on to the case study, fourth case study in the fourth unit. So what do you mean by electromagnetic induction? So the word itself, you will get it. You just cut it into three words. Start from the central word. What is it? Magnetic. Whenever there is a change in magnetic field, an EMF is induced. Central word, second or third word, whichever you are interested, you can just connect it, you will get electromagnetic induction. So whenever there is a change in magnetic field, an EMF is induced. If there is an EMF, we know that a current will be there. Without any battery or without any source of EMF, we are getting the EMF. That is the main thing here. So it is defined as the protection of an electromotive force, that is EMF, across an electric conductor in the changing magnetic field. The discovery of introduction was done by Michael Faraday in the year 1831. Electromagnetic induction finds many applications such as in electrical components, which includes transformers, inductors, and other devices such as electric motors and generator. I would say one more thing. That means for the production of the electric current and the transmission, that are the main things we can say. Why? Because you just think about if there is no current, can we communicate like this? No. And nowadays, in this pandemic situation, you are attending your class, the school, right? You are attending the online classes, all because of this current. If the current is not there, just think about it. So, to produce the current, to generate the power, and for the transmission, main thing we can say AC generator and transformers, we are using this principle, electromagnetic induction. And we can say whenever you are just using electric current, you can just think about our famous scientist Michael Faraday. That is why we are just, what we are calling it as father of electricity. So let us move on to the second paragraph. Alternating current is defined as an electric current which reverses in direction periodically. Alternating, that means changing. Changing in equal intervals of time, we can say. That is why in India we can say 50 hertz is our frequency of AC. In most of the electric power circuit, the waveform of alternating current is a sine wave. Sine wave means it is changing according to the function of sine. Actually, cosine also we can use it, but usually we will write sine omega t. What is the equation? E is equal to E0 sine omega t. I is equal to I0 sine omega t. Like that, we will say that. So, that is why we can say in the waveform means sine waveform like this. The waveform we are using is mainly sine waveform. So, let us move on to the questions. How to increase the energy stored in an inductor? How to increase the energy? What is the equation for energy? Half Li squared. 1 by 2 Li squared. L is the inductance and I is the current. So how will you increase the energy stored? And this equation is very important. Half Li squared. Which is the form of energy stored in the inductor also, you should know that. It is magnetic potential energy. It is magnetic potential energy. So how will you increase it? We can say the equation is half Li squared. If you are 4 times, we have to increase. If you are increasing the current by 2 times, doubling the current, what will happen? 2I the whole square. So if it is 2I the whole square, it is 4 times it is increased. So which is the option? The first option, by doubling the current. Okay. Now let us move on to the second question. Consider an inductor whose linear dimensions are tripled. If the linear dimensions are tripled and the total number of turns per unit length is kept constant, what happens to the self-inductance? The equation for inductance L is equal to, we can say, mu 0 n squared IAL. Mu 0 n squared IAL. L, we are increasing. Linear dimension, if you are increasing, tripled. And other things keep constant. Which are the things? We can say mu 0 remains constant. N remains, N means the number of turns per unit length remains constant. Area also remains constant. So what will happen? The answer will be linearly. It is, if it is increasing, length is increasing, inductance also increasing. So 3 times it is increased, tripled means 3 times. So the answer will be 3 times. Of course, the answer will be 3 times. The answer is B. Now let us move to the third question. Lenz's law is based on which of the following conservation? Lenz's law is based on which of the following conservation? It is charge, mass, momentum, energy. No doubt, and it's very, very important also, it is energy. Why? Because energy, we know that what is energy? Energy can neither be created nor be destroyed. It is the law of conservation of energy. According to Faraday's first law or second law or first experiment or second experiment, we are just seeing a coil and a galvanometer and a magnet is connected. A magnet is also there. When a magnet is moved, the galvanometer shows a deflection. Without any source, we are getting the current. So according to the law of conservation of energy, it is not suitable. But Lenz's law states that this induced current always opposing the applied current or the cause, the reason of the applied current. It can be, the reason can be, what is it, the movement of the magnet or movement of the coil. Here we can say movement of the magnet. So they will oppose the magnet. So from that, we can explain the law of conservation of energy. We can verify the conservation of energy. So this law only helped to verify the law of conservation of energy. That is very, very important. The topic name it is given in your textbook is Lenz's law and the conservation of energy is very, very important. So the answer here is the fourth one, that is D, energy. Now let us move on to the fourth one. What will be the acceleration of the falling bar magnet which passes through the ring? One ring should be there such that the ring is held horizontally and the bar magnet is dropped along the axis of the ring. If this is just consider a ring like this, we can just, it is a ring and what is it, a bar magnet we are just what is it, keeping in this manner. So if this is the axis and we can say dropped along the axis of the ring, what will happen? We will just read the options first of all. It depends on the diameter of the ring and the length of the magnet. Is it so? Acceleration. It is equal to due to the gravity. It is less than due to gravity. It is more than due to gravity. So let us move on to the first. We can just avoid it. Why? Because it is not depending on the diameter and the length. Now we can go for the 3 options given here. It is equal to gravity. If it is freely falling, we can say it is equal to gravity. But it's not falling freely. It is moving in the axis of the ring. So what will happen? We can say that some EMF will be induced here. This EMF will oppose the motion of the magnet. So it should be less or more. We can say anyway it is not equal. So we can say the answer is less than due to gravity. Acceleration will be less than due to gravity. So the answer option is C. So thank you children. Thank you for watching. And thank you 1 mark for giving a chance for discussing this 1 mark here. Thank you.